Hi, this is Alex from devstories.eu. Astropy, Python for Astronomy, Episode 12 of 15. In many scientific libraries, the mathematical equation you want to evaluate is tightly coupled to the algorithm used to optimize it. If you want to change how the optimization works, you often have to rewrite the way you defined your math. Astropy eliminates this problem entirely with its approach to analytical models and fitting. The core design philosophy of the astropy modeling subpackage is a strict separation of concerns. The mathematical definition of your equation is one object. The algorithmic engine that fits that equation to your data is a completely separate object. This means you can define your math once and then test it against several different fitting algorithms simply by passing the model into a different fitter. Astropy provides dozens of predefined mathematical models. If you are modeling a steady trend, you use a linear 1D model. If you are studying an emission line in a spectrum, you reach for a Gaussian 1D model. These model objects encapsulate their parameters, such as the amplitude, mean, and standard deviation. Before we look at the fitting process, we need to address a frequent source of confusion. In astropy, models are callable objects. You pass an array of coordinates directly to an instantiated model, and it evaluates the math to return the corresponding values. Most importantly, when you optimize a model, the fitter does not mutate your original starting object. It always returns a brand new fitted model instance. Your original guess is preserved exactly as you defined it. Consider a scenario where you have noisy one-dimensional array data representing a spectral feature. First, you initialize a Gaussian 1D model with your rough initial guesses for the amplitude, mean, and width. Because astropy separates the math from the optimizer, you attach your physical constraints directly to the model parameters. Suppose you already know the exact center coordinate of this spectral line. You access the mean parameter on your model and set its fixed property to true. The optimization algorithm will now leave that value alone. You can also establish mathematical boundaries. By setting a minimum bound of 0 on the amplitude parameter, you force the algorithm to reject any solutions that result in a negative peak. With your starting model fully constrained, you bring in the fitter. For nonlinear equations like a Gaussian, you instantiate the Levenberg-Marquardt-Weist squares fitter, known in astropy as Lev-Mar-LSQF fitter. You execute the fit by calling this fitter object, passing in your initial Gaussian model along with your horizontal and vertical data arrays. The algorithm runs and outputs a completely new Gaussian 1D model containing the optimized parameter values. Because this new model is directly callable, you just pass your original horizontal array into it to generate a smooth mathematical curve that you can plot against your noisy data. Here is the key insight. By storing constraints on the model rather than passing them to the solver, the fitting algorithms remain generic. You spend your effort encoding the physical reality of your problem into the mathematical model, allowing astropy to swap out the optimization logic in the background without breaking your pipeline. That is all for this one. Thanks for listening and keep building.